Ever feel like some people just lucked out in the looks department, like they won some kind of genetic lottery?
Totally.
Or maybe you've gone down the rabbit hole of beauty tips and tricks online, and you just feel like, what even is beauty anyway? Like the standards are always changing.
Right.
It's impossible to keep up. So today we're going to tackle something a bit different. We're going to see if there's a deeper reason, something more, you know, fundamental to why we find certain faces attractive. And you actually stumbled upon a really interesting research paper that kind of suggests that beauty could have a hidden, almost like a blueprint or code to it.
Yeah, yeah. It really is a fascinating paper. I think you hit the nail on the head when you said that beauty can feel so fleeting and subjective.
It does.
But this paper is called Facial Beauty Analysis Based on Geometric Feature toward Attractiveness Assessment Application. And it makes you think, well, maybe there is a more objective structural basis to beauty that we don't always realize.
I love that. So in this deep dive, what we're really trying to do is explore this core idea, right? Can we actually break down facial attractiveness and even judge it based on the pure geometry of our features?
Uh-huh.
Like, forget about makeup trends or perfect skin for a second and just look at the shapes and proportions themselves.
Right, and potentially we could come away from this deep dive with a totally new understanding of what makes a face appealing.
Exactly. It's not just about personal opinions. It's about finding those potentially measurable factors in something that honestly feels so personal and subjective.
For sure. Get ready for some interesting, sometimes maybe even surprising, perspectives on the science behind why we find certain faces beautiful.
I'm ready. And it's really interesting because the paper doesn't just start with, like, the latest technology. It actually goes back in time.
It does.
It talks about how ancient thinkers in China and in Greece, they were already trying to understand beauty through proportions and measurements.
Yeah.
They were looking at faces and trying to figure out what made them beautiful based on these, almost mathematical relationships between the features.
And it's amazing, right? This idea, this whole concept of beauty being linked to things like harmony and proportions,
Yeah.
it's not something new. It has these really deep historical roots.
Not just a fad. It goes way back.
These ancient scholars, they were convinced that there was an order to beauty, that it wasn't just random. They were looking for principles, mathematical principles, that they believed could be found in the natural world. And those principles, they thought, were reflected in beautiful faces.
It's fascinating, right? Because fast forward to now, and the paper highlights two main approaches to studying facial beauty that we've been using in more recent times.
Yeah.
And one of them is kind of, building on those ancient ideas about proportions, but using much more advanced tools and techniques.
Exactly. One modern approach essentially picks up where those ancient scholars left off. They take those old ideas about proportion and apply super sophisticated techniques to them. And a great example that they mentioned in the paper is the Marquardt beauty analysis.
Interesting.
And this analysis uses something called a golden decagon mask. It sounds kind of, science fiction-y.
It does.
But basically, you can think of it as a template. It's a template that's based on the golden ratio, which is this mathematical proportion that's often found in nature.
Oh, I've heard of the golden ratio.
Right. And so the idea here is that the closer a face's measurements match this golden decagon mask, this template, the more attractive it's considered to be.
So it's like they're saying there's a perfect blueprint for facial beauty, and that blueprint is based on this golden ratio.
Exactly. And the paper mentions some research that suggests this golden ratio template might hold true across different ethnicities and even different time periods.
It's crazy to think that something so seemingly objective, like a geometric shape, could actually be tied to something as subjective as beauty. But that's just one side of the story, right? The paper also highlights another important approach to studying beauty: psychological and social science research.
Right, exactly. That's where we get into how people actually perceive beauty.
Yeah.
And, initially you might think, well, that's got to be entirely subjective,
I
right?
think, yeah.
But even there, even in that realm, researchers have discovered some really interesting patterns. And one of the most well-known patterns is this idea of the average face.
Oh, yeah, I've heard of that. Like, if you take a bunch of faces and morph them together.
Exactly. Studies have shown that if you take a bunch of different faces and you digitally blend them together, the resulting image, the composite image, often gets rated as more attractive than most of the individual faces that went into making it.
That's so weird.
It is kind of strange. But there's a theory that our brains prefer what's familiar.
Okay.
And by averaging out a bunch of different features, you end up with a face that feels kind of, prototypical, like it doesn't have any extreme features. And that familiarity could lead to us finding it more attractive.
So it's almost like our brains are saying, okay, this face is kind of like a comfortable average. I like it. But it gets even weirder, right?
Oh, it totally does.
Because the paper also points out that the average of attractive faces
Yes.
is considered even more attractive than just the average of, any faces.
Right, and that's really fascinating, right?
What does that tell us?
It suggests that it's not just about being average in a general sense.
Mm.
It's about possessing those specific features that we already find appealing. And when you average those appealing features together, you end up with something that's super attractive.
So it's like there's a certain set of features that our brains are wired to find attractive, and averaging those features just amplifies that effect.
Yeah, that's a great way to put it. And then on top of the average face phenomenon, there's also symmetry.
Right, symmetry. Everyone always talks about how important symmetry is for beauty.
And for good reason. Psychological studies have consistently shown that symmetrical faces are generally rated as more attractive than asymmetrical ones.
Interesting. So we've got these historical geometric principles. We've got insights from psychology about how our brains perceive beauty. But now we're entering the age of technology. And the paper talks about how computers are now being used to analyze beauty in totally new ways.
Absolutely. And this is where things start to get super exciting, I think, because now we have the power of, huge data sets and really complex machine learning algorithms that can help us analyze facial beauty on a scale that just wasn't possible before.
Right. We've got all this data at our fingertips.
And computers can pick out patterns in what makes a face attractive that humans might not even consciously realize are there.
That's wild.
So it's like we're uncovering these hidden codes of beauty, if you will, with the help of these machines.
And this is not just some abstract research that's happening in a lab somewhere, right?
Yeah.
The paper mentions some real-world applications for this kind of technology, like in plastic surgery,
Right.
or even dating apps, or even just, making ourselves look better on those video calls that we're all doing these days.
It's true. Imagine a world where we can digitally enhance our images based on these scientifically backed principles of beauty.
It's both fascinating and, a little bit unsettling at the same time.
Oh, definitely. I think it opens up some ethical questions that we need to think about carefully.
Absolutely. But, this all leads to the central question that this particular paper is trying to answer, and it's a big one.
Yeah.
What is the core essence of facial beauty? Like, what's that fundamental quality that stays the same, regardless of whether someone's wearing makeup, how old they are, or even what the latest beauty trends are?
And they're specifically looking at the geometric features of the face, the shapes and proportions.
Right, because those features are less influenced by all of those temporary factors. It's like trying to strip away all the changeable stuff and get to the core of what makes a face structurally beautiful.
Exactly. And that's a really ambitious goal, right? Because how do you even begin to measure something as complex as facial geometry?
That's what I was thinking. It's not like you can just take out a ruler and measure someone's nose and say, okay, you're good to go.
It's way more complicated than that. But in this study, they use this really interesting system of what they call 2D landmark points on the face.
Okay.
And they map out 68 very specific points on every face they analyze.
Wow, that's a lot of points.
It's like placing tiny digital markers at key locations around the eyes, the nose, the mouth, even along the outline of the face.
So they're basically creating this detailed map of every face based on these 68 points.
Precisely. And each point gets represented by its X and Y coordinates, like on a grid.
Okay, but wouldn't that be really sensitive to, like, how the person's head is tilted in the photo or how close they are to the camera?
That's a really important point. You're absolutely right. If you just took the raw coordinates, those measurements would be affected by all sorts of things. Like if the person tilted their head, if they moved closer to the camera, the coordinates would change, even though the shape of their face hasn't actually changed.
Right.
So to get around that, they use mathematical transformations to make those geometric features invariant.
Invariant.
Which basically means that no matter how the face is positioned in the image, the underlying geometric information stays the same.
Oh, that's clever. It's like they're digitally standardizing all the faces.
Exactly. It's like aligning all the faces in the same way so that they can be compared fairly based purely on their shape.
That makes a lot of sense. So they've got this system for measuring facial geometry in a really precise and consistent way.
Right. And they actually use that information to come up with this really interesting concept called a geometric beauty score.
A geometric beauty score, what's that exactly?
Well, it's this really intriguing idea. They're trying to figure out the highest possible beauty score a face with a specific geometric shape could get. And they do this regardless of the skin texture or makeup or any other changeable feature.
So they're trying to isolate how much the shape itself contributes to attractiveness.
Yes, exactly. Like, imagine you have a face with a specific bone structure. What's the maximum level of attractiveness that face could achieve if everything else was perfect? That's what the geometric beauty score is trying to represent.
It's like trying to find the inherent blueprint for an attractive face,
Right.
independent of all the little details that can change.
Yeah, pretty mind-blowing, isn't it?
It is. But how do they even determine what makes a shape more attractive?
Right, that's the big question. And this brings up another challenge. In order to train their model, they needed a way to get reliable beauty labels for faces.
Meaning they needed to know which faces were considered attractive and which weren't.
Exactly. But getting those labels is tricky because beauty is so subjective.
Oh, yeah. You can't just ask a few people and assume that's the definitive answer.
Right. Asking a ton of people to rate thousands of faces would be really time-consuming and expensive, and it might not even be that accurate.
Mm. So what did they do?
Well, they came up with a very clever approach. They used what's called a semi-supervised approach.
Semi-supervised, meaning they used some data that was already labeled, but also incorporated some unlabeled data.
Exactly. So for the most attractive faces, they looked to the internet, specifically images of famous actors and actresses,
Okay.
because those are people who are generally considered to be attractive by a large audience.
Right. So it's like using a shortcut to get a set of faces that are generally considered to be beautiful.
Exactly. But then the question is, how do you get the most geometrically unattractive faces? You can't really ask people to point out the least attractive faces. That would just be awkward and kind of mean.
Yeah, it would be.
So here's where their methodology gets really creative. They generated the most geometrically unattractive faces by algorithmically distorting real faces.
Wow.
Basically, they took real faces and used algorithms to exaggerate certain features, to make them disproportionate, or to violate basic principles of facial harmony.
So they intentionally made them less attractive by messing with their proportions.
Exactly. Their thinking was that if you move too far away from the average face, you're likely to end up with something that's less attractive.
It's like creating those exaggerated caricatures of people, but instead of making them funny, they're making them less attractive.
Precisely. And they even had human raters confirm that these computer-generated faces were actually unattractive.
That's a smart way to make sure their method was working. So they've got these extremes, the most attractive faces from famous people, and then these intentionally unattractive faces created by the computer. But what about all those faces in between? Those everyday faces that aren't super attractive, but aren't super unattractive either.
Right. So for that, they used faces from a large real-world database. This database had a bunch of faces from Shanghai, and they treated those faces as unlabeled in terms of beauty.
Okay, so they have these labeled extremes, the really attractive and the really unattractive faces.
Right.
And then they have this big pool of unlabeled faces.
Exactly.
So how do they use all of that to actually build a model that can predict beauty scores based on geometry?
This is where it gets a bit more technical, but I'll try to explain it in a way that makes sense. The core of their method is this new algorithm that they developed, and it's called Hessian Semi-Supervised Learning.
Hessian Semi-Supervised Learning. So it's semi-supervised because it's using both labeled and unlabeled data.
Exactly. And Hessian refers to a type of mathematical matrix that's used in the algorithm.
Got it.
The goal of the algorithm is to learn a function, what they call a beauty score function. They can accurately predict the beauty score of any face based on its geometric features. And the way it does this is by leveraging this really interesting concept called a geometric feature manifold.
A geometric feature manifold. Okay, what in the world is that?
It's a really cool idea, actually. Imagine a space, like a multi-dimensional space, where each point represents a different face shape. And similar face shapes are closer together in this space. So faces that are more similar geometrically would be closer together.
Okay, so it's like a map of all possible face shapes,
Yeah.
and the closer two faces are on the map, the more similar their shapes are.
Exactly. And what this algorithm does is it uses the labeled attractive and unattractive faces as kind of anchor points in this manifold. It uses them to figure out where those extremes of beauty lie in this geometric space.
So it's using the actors and actresses' faces as a reference for where beauty lies on this map. And it's using those distorted, unattractive faces as a reference for where the less appealing shapes are.
Yes, exactly. And then it tries to understand the overall structure of this manifold and predict where those unlabeled faces fall on the spectrum of beauty between those two extremes.
That's really cool. So it's not just looking at individual measurements, but it's looking at how different shapes relate to each other within this whole universe of possible face shapes.
That's a great way to think about it. And it actually worked really well. They tested it out on a couple of different data sets, and they found that their algorithm was really good at predicting beauty scores based purely on geometry.
Well, that's what we want to know, right? Like, does it actually work? What were the results?
So they had two main data sets. One was their own data set, which they call the Geometric Facial Beauty Dataset, or GFB for short.
Okay.
And it had a mix of Asian male and female faces.
Okay.
And then they also used an existing database called the Multimodal Beauty Database.
Multimodal beauty, MB.
Exactly, which had Western and Eastern female faces. So they wanted to test their algorithm on different types of faces.
That makes sense. You want to make sure it works across different populations.
For sure. And on their own GFE dataset, their average mean squared error of prediction, or MSE, was about 14.9% for females and 9.88% for males.
Okay, so what do those percentages mean?
Well, it means that their model was pretty accurate at predicting the geometric beauty score. The lower the MSAP, the closer the model's predictions were to what they should be based on the training data, those attractive and unattractive examples they fed it.
Okay, that's good news for their model. And how did it compare to other existing methods for predicting beauty?
So they compared their Hessian Semi-Supervised Learning algorithm to a bunch of other common machine learning algorithms like k-nearest neighbors, ridge regression, artificial neural networks, support vector regression, all those kinds of things.
Yeah.
And the results showed that their algorithm was really competitive, and in many cases it actually outperformed those other methods at predicting facial beauty based just on geometry.
So their specific approach is really promising.
Exactly. And to make it even more visual, they actually tried to visualize the distribution of faces in this geometric space.
Oh, wow. How did they do that?
They use a technique called locally linear embedding, which is a fancy way of reducing the dimensionality of data. They took all those complicated geometric features and squashed them down into a 3D representation that we can actually look at.
So they created like a 3D map of face shapes.
Exactly. And when they looked at this 3D map, they found that the attractive faces were all clustered together in one area, and the unattractive faces were clustered together in another area.
That's really cool.
Yeah, it's like visualizing those clusters of beauty, and all those unlabeled everyday faces, they were kind of spread out in between those two extremes.
Which makes sense. Most people fall somewhere in between those extremes of beauty.
Exactly. But they didn't stop there. They actually identified the top 5 most geometrically attractive and the bottom 5 most geometrically unattractive faces from their Shanghai database based on their model's predictions.
So they found the most and least attractive faces based purely on their shape, according to the model. That must have been fascinating to see.
It was. But to really isolate the effect of geometry, they went a step further.
Okay.
They took those faces and created beautified versions of them, where they kept the original geometric shape, but they replaced the texture and the other changeable features with the features from attractive faces.
Oh, I see what they did there. So it's like they're saying, okay, let's take this unattractive shape, but let's give it perfect skin and see if that makes a difference.
Exactly. And what they found is that even when you give an unattractive face those perfect features, if the underlying shape is still considered unattractive, it's still going to look less appealing overall.
So the shape is really important. It's not just about having nice skin or symmetrical features. It's also about the proportions of your face.
Exactly.
And vice versa. You can have, less than ideal skin, but if you have that geometrically attractive shape, it still shines through.
Right. But they wanted to make sure that their model wasn't just some mathematical abstraction. They wanted to see if it actually aligned with what humans find attractive.
So how did they test that?
They did a really cool experiment where they showed pairs of those geometrically purified faces to human raters. Remember, these faces all have, the same great skin and features. The only thing that's different is the underlying geometric shape, that score that the model came up with.
Okay, I'm following.
And they simply asked the raters, which face in each pair do you find more attractive?
So the raters are only judging the shape because everything else is controlled for.
Exactly. And what they found is that the model's predictions matched up with the human's choices pretty well.
Wow.
For female faces, the accuracy was 84.21%, and for male faces, it was 81.47%.
That's a pretty high level of agreement.
It is. And it suggests that this model, which is based purely on math and geometry, is actually picking up on something real about how we perceive beauty.
So it's not just a coincidence. There's something to this idea of geometric beauty.
Right. But they also found something else that's really important.
Yeah.
Even though there was good overall agreement, there were still disagreements among the raters.
Meaning not everyone agreed on which face was more attractive.
Exactly.
Huh.
And this highlights that beauty is still subjective, even when it comes to something like geometry. They actually measure this. They call it raters' agreement between each others, or RAE.
So they're quantifying this subjectivity of beauty.
Yeah. They're showing that even though there are some general principles that most people agree on, there's still a lot of individual variation in what we find attractive.
So maybe it's unrealistic to expect that we'll ever find a single formula for perfect beauty.
Yeah, I think that's a really important takeaway. Beauty is a complex thing. It's influenced by all sorts of factors, both biological and cultural, personal and universal.
So what are the implications of this research? Like, where do we go from here?
Well, I think this study has opened up some really exciting possibilities. For one, it shows that we might be able to use deep learning and big data to study beauty in a more objective way without having to rely so heavily on subjective human ratings.
That's huge. It could really speed up research in this area.
Exactly. And it also suggests that there's still a lot more to learn about how we perceive beauty. They specifically mentioned that future research should look at how facial expressions influence our judgments of geometric beauty.
Right, because a smile might make a certain face shape look more attractive than it would if the person had a neutral expression.
Right. So there are all sorts of interesting avenues to explore.
So, to sum up our deep dive into this fascinating world of geometric beauty, it seems like there really are some fundamental principles at play that influence how we perceive attractiveness.
Yeah.
And these principles go beyond just, having smooth skin or symmetrical features.
And what's exciting is that this study provides us with a framework, a way of actually quantifying this geometric beauty.
It's moving us beyond this vague idea that beauty is just in the eye of the beholder and toward a more nuanced understanding of what makes a face beautiful.
Exactly. It's really pushing the boundaries of how we think about beauty and attractiveness.
And that's what we love to do here on the Deep Dive.
For sure.
I hope this deep dive has sparked some new ideas and maybe even some new questions for you listening. If you want to go even deeper, we encourage you to check out the original research paper. We'll include a link in the show notes. And please, let us know what you think. What stood out to you? What other questions do you have about this whole idea of geometric beauty? We'd love to hear your thoughts.
Yeah, join the conversation.
Because this is a topic that's constantly evolving and there's still so much to discover.